Evening, guys. I guess I'm loud and clear to all of you. First, before we get started with today's session, guys, you can understand today we'll be completing the entire chapter of hydrogen. It would be kind of a crash course, so you can say one shot. Um, in this topic, I would be mainly focusing on, see, there are different levels of studying one chapter. Right now, my main focus would be teaching you this chapter because you can understand it is in J advanced, right? So the notes that I have made for this chapter, this is going to be more than enough for your JE advanced preparation. And I have been keeping few things in mind before making this notes. One and the most foremost important thing is the previous year questions of JE advanced that has been coming. You cannot expect a lot of question coming from the chapter hydrogen because they gave a question entirely from inorganic chemistry, which is a mixture of question in the advanced, right? They don't focus in one or two questions. It's always mixture of 4 to 5 chapters in there, right? So it's the same thing that happens for hydrogen as well. If you look at the PYQs of GFANs, that they have mixed it with any, P block chapters, or let's say any S block chapters, or let's say sometimes they have also mixed it with the basic concept of chemistry chapter as well. So you can understand it's the overall level. An isolated question of this chapter is something less likely to be found. Okay. Now, the point is right now, my focus will be completely teaching you in the advanced level, but yet again, guys, the time is a constraint over here. You can understand that. So I've been going a little fast, but and the most of the things will be written in the notes only. All right. So I'll be sharing these notes with you. So no need to take the pain of writing this alongside whenever I'm teaching you here. Right now in the class, just try to understand whatever I'm saying here, and I'll be sharing the notes with you. In this notes, it is self-sufficient. You read it, you will be able to understand everything in there. So you don't need to take additional notes for yourself. All right. So now let's get started. First, guys, I want all of you to turn on your cameras before we get started with it. Come on, guys, make it quick. We are already having a lackage of time right now. Let me have a quick look of the class. Quickly, guys, turn your cameras on. If there's something that's stopping you from doing that, let me know. Aditya, Janani, quickly. Mathira, Arnav, Musika. Okay, guys. All right. So, all right. Like I said, guys, in this chapter, you don't need to take any notes whatsoever. Focus on whatever I'm trying to say. Try to understand this part. It is inorganic chemistry. So there is a kind of, conception that we have in for inorganic chemistry. We might have to mug a lot of things up. Okay. So don't have these kind of pre-quizzes conceptions like that, guys. Everything has a logic in here, and we'll be trying our best to learn this topic in that way. Okay, whatever I'll be teaching you this, guys, it would be needed in a followed up chapter like P block, S block, and one of the most important chapter of grade 12, which is there in your board syllabus as well, which has the name of D and F block. Okay, which is the like all the exceptions that you hear about chemistry, they are actually coming from those D and F block chapter, right? So make sure you focus on the concepts more, try to understand it better. All right. When you have any doubts or something, guys, I would be taking all of your doubt after the session or during the session also. You can write it down for me in the chat section. Okay, I'll be taking a few minutes in order to answer your questions, guys, but I would definitely answer all the questions in here. All right. Now, guys, whenever you're sending a message, make sure you're sending it to the host. All right. Now, let's get started then. So, here, guys, first of all, we are learning about the chapter hydrogen today. Okay.
Mm.
In
Excuse me,
this
sir.
chapter, we have a lot of reactions to go for. And in the end of the chapter, there is something very, very important that we are going to go for. It's called the hard and soft nature. Yes, Pratyush, you have a question for me?
Yes, sir. Will we make notes or it will be available somewhere?
Like I said, this note I'll be sharing with you. Don't take the pain of writing this anymore because I'll be going a little fast because I have only 2 hours to complete this chapter, right?
Okay, sir.
Don't write anything in here. And guys, this note is self-sufficient till your JFMs. So no need to worry about that either. Now, so guys, first, like I was saying, we'll be talking about the different type of questions from here. And there is one question from hydrogen chapter that is being combined with basic concept of chemistry in JE Advanced, and it is a PYQ. I'm going to show you that question as well. Okay, one sec. It's in our it's in your notebook, Ashita. I'll be sharing with the others as well. It's in your notebook under the hydrogen segment. Okay. Now, guys, first of all, I don't have to tell you which all isotopes that we have for hydrogen. We have protium, deuterium, and tritium. We all know about them. And the most abundant is definitely protium. Guys, more than 99% is what you have this abundantly. This guy is over there for 0.016% or something close to that. Whereas tritium, which is actually the only radioactive isotopes out of all these three, this is radioactive, guys. And the availability of this is 10 to the power minus 15. You can understand how small the availability is, percentage, I'm saying. All of these things are in percent. Okay, so only tritium is our radioactive isotope out of all. Now, there is something for hydrogen that has been frequently being asked from hydrogen chapter, even in JE mains as well previously. Right now, you don't have it. So, what is orthohydrogen and what is parahydrogen? There is nothing clearly written in the NCRT about it. It is just mentioned. Now, guys, I'm going to give you a clear idea about what is ortho and parahydrogen. Room temperature. Okay, I'm going to explain this thing. Okay, so guys, there are two types of hydrogen on the basis of the nuclear spin. Again, what all doubts if you having, guys, will be taking this in the end of the session. Okay, write that in the chat for the time. So, ortho and the parahydrogen, it is based on, for those who are taking my session for the first time, guys, whenever I be writing something, I'm looking at my left hand side. I have another screen there. So, nuclear spin, based on nuclear spin, there are two types of hydrogens in there. One is called orthohydrogen, another one is parahydrogen. It has nothing to do with the ortho and para of benzenoid systems. They are not the same, guys. Here, if you see, I have taken a picture over here for you. Like when the proton spins, you know that protons and electrons, they are all, what should I say? Electrons are fermions, you know that protons, electron, all are coming under the fermions, right? Now, they would be having their own spin. So if you look into the spins of protons over here for the ortho and the para hydrogens, guys, for ortho hydrogen, what we see is the spins are on the same side, same direction. So it's the same like, guys, you have learned for electrons plus half minus half. It's the same like that. When the spins are on the same side, let's say clockwise direction or anti-clockwise direction, however you want to do that, then we call them orthohydrogen. And whenever the spins of the hydrogen or protons of hydrogen, one is in clockwise, another one is in anti-clockwise, that is called parahydrogen. So guys, you can understand I'm talking about hydrogen molecule right now. Hydrogen molecule is made up of two hydrogens. No? So orthohydrogen means when both the hydrogen are in the same spin, and para means when they are in the opposite spin. Right now, guys, that's the quick question. Looking at this situation, which hydrogen is more stable? Write it down in the chat. Which hydrogen looks like more stable, ortho or para? Very good. Many of you are right, but there are some silly mistakes that has been done as well. Guys, para hydrogen is more stable, right? Opposite spin are always stable because they cancel out the magnetic characters, right? So because of that reason, para is more stable. Now, what happens is if you look at hydrogens at 0 degree centigrade, when you look at 0 degree centigrade, there you have high abundance of para, high abundance of para, because the molecule is definitely like to be in the para state. But more you give energy to it, Hanshika, what would happen? It would give you more and more ortho abundance in there. So when you increase the temperature from this point beyond, guys. So let's say I'm talking about room temperature. At room temperature, para is 3 times. Ortho. Not even in room temperature, even beyond that. Let's say we go beyond the room temperature. Okay, there is another statement which goes, this is also a question that came in the advanced only, guys. Um, what is the what is the abundance of ortho is to para? This would be 1:3. Ortho is more, para is less. Ortho is to para at the temperature at which liquefaction liquefaction of gases are done. So at the temperature when liquefaction of gases are done, that means, guys, in a easier terminology, we can consider this to be the higher temperature. So there also you can consider this the, just one sec. Ortho would be more, para. So more you increase the temperature, guys, your ortho abundance goes higher up, para abundance goes down. All right. So this is about the ortho and para hydrogens. This much is fine. All right, guys. Now, going on to the next one about the properties of hydrogen. Guys, now we are going to go for the different reactions. Okay, if you open the NCERT, they are going to talk about physical properties and chemical properties different. All right. Right now, I'm going to just teach you the chemical properties because, guys, physical properties of hydrogen talks about whether it's a gas or not, or it's a boiling point or it's a melting point, these sort of things. We have never seen question coming in from there. So let's go for the chemical properties thing. In here, we are going to learn about different reactions and how the hydrogen is being formed, in which all reactions through which we can make the hydrogens. First is how hydrogen reacts with different metals. So guys, you can clearly understand over here, Vignesh. Let's try to understand this thing. If I talk about a metal's electronegativity with respect to hydrogen's electronegativity, we all know that, David, that for metals, the electronegativity is, they are literally called electropositive element, isn't it? Because their electronegativity is even lower than 1. If I talk about sodium, what is the electronegativity value? 0.98, correct? So that means it is lower than 1, correct? So they are electropositive element. And what about hydrogen, guys? For hydrogen, it is exactly, for hydrogen, it is electronegativity value is 2, correct? Right answer, Smriti. So for hydrogen, if it is 2, and for metals, if it is less than 1, so you can clearly understand, guys, when metal and hydrogens are combining together, the metals are going to be positive, cation, and hydrogen is going to be anion. Right? What I mean to say is, Swaraj, let's say I'm talking about HCl. How do you break HCl? H plus Cl minus. But let's say I'm talking about NaH. How are you going to break it? Na plus H. While teaching you in hydrocarbons, guys, I taught you hydride shift. At that time, I told you guys, we call this as the hydride because it is containing a negative charge on, right? So there is a famous question that comes that has been coming in JEE mains as well, which is, if you take a metal hydride and electrolyze it, where would you find the hydrogen gas? So guys, if you electrolyze it, then in the metal hydride, hydrogen is an anion. So where would an anion go? The anion would go to anode. People would write capital because they think hydrogen is cation. They are not for metal hydrides, guys. They are anion. Now see, metal hydrides are also called ionic hydrides for this reason. Ionic, or you can also call them saline hydrides. Why saline? Because saline water means NaCl water, right? Salt. So from there, a saline means ionic compounds also. All right. So that's why the saline hydrides or ionic hydride is what we call. So they make ionic compound. Now, just one second. All right. So in this part, um, okay, we call them ionic hydrides because of ionic compound are getting formed here from the metal hydride systems, and we also call them saline hydride because it's a like we call it like colloquial language. In that we call it saline hydrate, because saline is nothing but initial water, right? So salt water. So in that way also we consider this as a salt in that way. Okay. Now, if I go beyond this, now guys, how are the hydrides, metal hydrides, like how is hydrogen gonna react with metal? So you know that whenever there's a metal oxide and hydrogen is reacting with it, hydrogen is a very good reducing agent. So you can clearly see it is itself getting oxidized here, but it is reducing the metal oxide to metal. In every single situation, it is gonna do the same thing. This particular method is also being used, like earlier it has been used to for the reduction of metals as well, right? You can clearly see that this is how, by using the hydrogens, you can reduce the metal oxides here, right? Going to write that, guys. These are very simple reactions out there. Now, in which all other ways it can act like reducing agents over here, guys? Definitely, you can see even for non-metal oxides also, if you react it with hydrogens, you can still get reduced products. As you can see, P2O5, it is turning into PH3. You don't have to remember these reactions, guys. I'm just trying to give you examples of how do they act like reducing agents. All right, very simple things. Whenever you are anything you are reacting with hydrogens, make sure that if it's an oxide or something, you reduce it and form water with it. Correct? So hydrogen turns into water, and non-metal, you write the most reduced version of it. So pH3 in here, right? Like that. Now, you can clearly see that it is even more, if it is, there is more some reactions I'm showing you for the alkali metal salts, how it is reducing. Again, guys, the same thing. When you are reacting hydrogen with different salt, again, you can clearly see that the alkali metals, they are also getting reduced. Like, how are we understanding this? Because you can clearly see that sodiums, potassiums, they are in +1 oxidation state, and in the elemental level, they become zero, right? So they are getting zero, and the it's complete as displacement reaction, as you can see, right? HNO3, HCl, and the other product, the better. So, in a nutshell, overall, hydrogen is something which is very much reducing in nature, right? Now, coming to the next part. Now, here, guys, what actually happens is when you react, now, how would you actually produce this hydrogen? Now, hydrogen can be produced through many methods. Yes, Pratyush?
Sir, I was having a doubt in the P2O5 reaction.
Right, tell me.
Sir, in the P2O5 reaction, if H is acting as a reducing agent, so it will
Mhm.
have positive charge, right?
Who would have positive charge? Hydrogen.
H, yes, sir, because it is giving,
Okay.
is gaining.
Okay. I want to hear the entire question out now.
Sir, so why H is on the right hand side? Why? Because when some H thing is acting electropositive, so it is on the left hand side.
Okay.
Sir, in
I,
pH.
oh, now I got your question. Okay. Very good. So what he is trying to ask us, guys, that if I talk about a cation, if I talk about a cation, then in that case we write the cation. If I talk about a molecule, we write the cation first and then the anion, right? In that way, we write them. So now he is asking me, sir, if hydrogen is acting like a reducing agent, then why is hydrogen an anion? Right? This is the question that he is trying to say. So, better if you see that, if you look at the oxidation states of all of these people. So, if you just look at the phosphorus over here, what is the oxidation state of phosphorus? Tell me. If you take it as X, 5 oxygen is 5 to the 10 minus 10, so it would be plus 5, right?
Yes, sir.
What is the oxidation state of phosphorus over here?
Sir, 3.
Plus 3, right? No, wait. It is
Plus.
minus 3 only. Check it one more time. Plus 3 or minus 3? It's minus
Uh,
3, right?
that only I'm, sir, confused about.
Huh. So, oh, you are confused about the oxidation state of it, right?
Because it is on the right hand side, so
Okay. In these kind of situations, there is a shortcut that you can follow. Let's say this is my pH3 molecule. Now you tell me, in between phosphorus and hydrogen, who is more
sir, hydrogen. It will. It is more phosphorus is more electronegative.
than hydrogen? Yeah, similar of them, but phosphorus would be having a little bit more than hydrogen.
Yes,
So
sir.
the electron would be trapped by phosphorus, no?
Yes, sir.
So negative charge would be on phosphorus. Hydrogen would be positive. Yeah.
Yes, sir.
So now I guess it's very good. Draco compound. Na? So now see, P2O5. So this is the reduction, I guess. Now it's clear.
Sir, but why hydrogen is on the right hand side if it is electropositive then?
Better, we are talking about right now. We are talking about this covalent compounds, right?
Yes, sir. Yes, sir, I
Right.
got it.
So if you talk about NH3, then also we write it's not a cation or anion. But for ionic compounds, we follow that method. The cation puts in anion. For covalent compound, we don't follow this, right?
Oh, okay, sir, got it.
Okay. Now let's talk about where was I, guys? Yes, yes, over here. So guys, how exactly, Ashita? Now, guys, try to understand this part. This is very, very important here. Later on in grade 12 organic chemistry, there'll be many situations, guys, where you would learn a topic called in situ. In situ. What do I mean by this in situ terminology? It means inside the reaction. So there are some reducing agents. So guys, this mixture, zinc and what sulfuric acid, this mixture acts like a reducing agent. Now, how is that possible? So they say that it forms it forms nascent hydrogen, NaCl, nascent hydrogen. Check the spelling once, guys. It forms nascent hydrogen in situ. This is the terminology that they are going to mention over there. What do I mean by that? Means within the reaction, it is going to make hydrogen. So right now in this mixture, you don't. C is there now. So in this mixture, there is no hydrogen, but guys, this mixture is a reducing mixture. Now, why is that? Because when you react them together, you get zinc sulfate and nascent hydrogen. Now, what is this nascent hydrogen, guys? Nascent hydrogen is atomic. When any particular species is in atomic state of it's a very, very strong compound at that moment. Like it's a very, very reactive state. Because guys, nothing is stable in their atomic state, so it wants to form a molecule right away. So the moment it sees any opportunity, it would just go and grab it and it would form a molecule of hydrogen with it. So that's why, guys, this atomic state, nascent means newborn. This atomic or this nascent state, it's a very strong reducing agent. It has a very high reducing character. I'm gonna show you more examples of that actually. Right now, we're just gonna stay with it. But later on, when I'll be teaching you bleaching powder, how is bleaching powder gonna bleach? Or let's say we talk about nitric acid's oxidation tendency. How do nitric acid act like an oxidizing agent over acidic properties? So, like if I talk about nitric acid, giving nitric acid to somebody, it acts more like an oxidizing agent rather than an acid. So why does that happen? So it's all because of this nascent properties. So I'm going to show you all those examples in there as well. But anyways, guys, when you react it with sodium, zinc, and aluminum, what you actually get is the hydrogen in the nascent form. That's why they are all reducing mixture. But here for sodium, guys, this reaction product is very, very important for us. You have learned that in grade 10 as well. I guess you remember sodium zincate and sodium aluminate or meta-aluminate, you used to call it. This particular reagent gives you sodium, meta, or normal aluminate, whatever you are comfortable to say. Meta aluminate or aluminate, right? Why do the atomic hydrogen? Very good, Samia. They both, it's like, see, these atomic hydrogens, they are just waiting to react with anybody, right? So if you want this mixture to act like a reducing agent, what you have to do is you have to give this mixture in a reaction medium. And what would happen is the moment this nascent hydrogen forms, let's say some of it would form molecules, but the rest of it, let's say 2% or 3% hydrogen would react anyway immediately with the molecule you want to reduce. That's the main point actually. Because see, every reaction has major product, minor product. So whatever you are saying, that is also there. But whatever I'm saying, that product is also not 100%, right? It would be like, let's say 60-40. It's like that. Better, huh? Clear? Guys, keep your cameras on. Now, moving forward, guys, methods of preparation. Very simple methods are there, guys. You have like you know about most of them. Right now, what happens when metals are reacting with water, guys? You already know that when metals and waters are reacting together, you get metal hydroxides and hydrogen gas. Correct? So whatever the metal is, you would always get hydroxide and hydrogen. There is something I need to tell you here. So when metal and water are reacting together, you get two types of products actually. Metal hydroxides in certain situations. In certain situations, you get metal oxides as well. But hydrogen gas is something which is common for. But now, guys, when do you get hydroxide and when do you get oxide? If your metal is highly reactive, if your metal is highly reactive, in that situation, you get metal hydroxides. But if your metal is weak or not strong enough, in that situation, you get metal oxides. Now, there comes the question, guys. How do I know that whether my metal is strong or weak? That's the question. Now, guys, in exactly Smriti, in grade 10, you have learned something called metal activity series, if you remember. There you learned that potassium is the most reactive metal, then sodium, then calcium, then magnesium, aluminum, zinc, iron, nickel, so on and so forth, hydrogen, copper, Ag, Au. The list just keeps on continuing like that, right? So you know that these elements, these metals, those are there, they are highly reactive. These are moderate, and the rest of them are not that strong metal. They are like the reactivity is going down. Now, guys, try to understand this particular example. Let's say I am talking to somebody who is highly reactive. Okay. In that case, if you want to react it with water, the water can be normal, still the reaction would happen. Correct? Let's say Smriti, I'm taking a normal metal, I mean highly reactive metal, and I'm just giving a normal water. Then the metal would react. But as the reactivity of the metal is decreasing, I have to increase the reactivity of the water there. So I have to heat the water up more and more, right? Temperature of the water needs to be increased. Exactly, Shika. So as you see, when we are taking sodium, calcium, potassium, in this situation, I'm just giving normal water, I'm getting hydroxides and hydrogen gas. When I'm going a little bit down below towards magnesium, if I'm giving water, I have to make it hot. Then only I'm going to get the hydroxides and hydrogen gas. But if I'm talking about iron, guys, I'm talking about weak metals now, right? It is down below, right, Vignesh? Right, Samya? So now in this case, Shrutika, what would happen? This would, first of all, it won't give you hydroxide, it would give you oxide. That's a separate discussion. My water has to be a steam this time. Even on the top, guys, my metal has to be red hot as well. So do you understand? We are trying to increase the reactivity by increasing the temperature over here. No, Swaraj, we are going to get something more than that actually. But appreciate the way you tried this. So now in this case, Subhangi, what we actually get is, you remember this particular reaction, guys? We get Fe3O4. What is this? Write it down. What's the name of this molecule? Fe3O4. Is it rust? Is it ferrous oxide or is it ferric oxide? What is it? Iron has two valence, 2 and 3. 2 is ferrous oxide, 3 is ferric oxide. It is neither of them. Or I should rather say it is both of them. And that's why we call it ferroso-ferric oxide. Ferroso-ferric oxide. It is both ferrous oxide and ferric oxide together. Exactly. Remember this one, guys? Red hot iron reacting with steam, right, Rohit? So now this is the situation for water. Now, guys, there are some industrial methods through which actually we can also form this hydrogen gases. Now, here, Hanshika, one of the most important methods in there is called Lean's process. There is another one called Bosch process. I guess that is not there even in your J advanced, I guess. No, that Bosch process is there in advanced. Bosch and Lean. Guys, do check it whether these two processes are there in NCRT or not. I don't really remember that. Okay. But from here, the questions have been coming there. Okay. So now, So over here, Daivik, lanes and bros, both this process of commercial method means in industries, Taran, how we make hydrogen. So that is what we are going to talk about now. Because in industry, it's not like only we need the product. In industries, we need the product in the highest extent and in the least amount of cost, right? So that was give us more and more profit. It's like that. So how do you get generation? How do you get the hydrogen over here? So first, guys, iron, red hot iron and steam. What would that give me? Fe3O4 plus hydrogen. See, in this simple method, you get the hydrogen. But guys, always remember one thing. Whenever you're reacting to things together and you're getting a product, this product is never 100%. It is never 100%. So you get a very like somewhere around 60% or 50%. And not only the product, guys, even the product's purity is also not that from chemical reactions. Like you don't know about it, but like whenever I have been performing any reactions in the lab, a reaction takes 1 day, but purification of the product takes near about a week because we always get a lot of byproducts, and the removal of byproduct is Shrutika is something that we have to pay more attention to, or we have to work more harder for this kind of thing. All right, um, guys, those who haven't kept their cameras on, I would like to know the reason why. Otherwise, keep it on. All right. Now, like I was saying here, in the first process, we'll be getting the hydrogen. Now, moving forward, this Fe3O4 is further utilized going forward here. How do you utilize this, guys? We take this Fe3O4, this byproduct over here, we take this and we react it with COH2 mixture. We call this particular COH2 mixture, famously it is known as thin gas. We call it thin gas. Now, why do we call it thin gas? Because, guys, this is being used in synthesis. This mixture is being used in synthesis of methanol. See, earlier, no, we do have those labs and all, and we didn't used to make all those kinds of organic molecules that the way we make nowadays. So at that time, if like there would be a very limited amount of resources that we used to have, and very limited amount of molecules is something that we used to make at that time. So that's why, guys, we used to give them some, like I said, some colloquial methods of writing of calling them. So syngas is coming from that for synthesis of it. Water gas, Apratim, is when you have CO and H2. I'm going to show you that as well, water gas and syngas. Okay. So anyway, my point is, um, now how do we form the syngas? So when you take a little bit of coal and when you react it with steam, that is when you get COH2. You get the syngas from there. Okay. Anyways, what actually happens is now, guys, when you react this Fe3O, guys, what is this metal oxide, right? Metal oxide. When a metal oxide is reacting with hydrogen, what is supposed to happen? It's going to reduce the metal oxide to what? To the metal and water. We have seen this before, right? Guys, later on in grade 12, there used to be a chapter which has been deleted now from your JEE main syllabus, which is called the purification of metals. I mean, I don't really remember the exact name of the chapter. The chapter is nothing but metallurgy, actually. Okay, isolation of metals. That was the name of the chapter. So, in the metallurgy chapter, guys, we learn which all reagents are actually being used in order to extract metals from their ores. In there, guys, we learn about three reagents that is famously being used for reduction of metals. One is aluminum, specifically, guys, aluminum oxide. That is one. That was there in red 10 as well. Exactly. Aluminum oxide, carbon monoxide, and carbon. These are the three reagents, guys. Those are being famously used, mostly used in order to reduce the metals from their ores or take it off. Carbonyl CO is also very, very good reducing agent, guys. Why is that? Think about why won't it be? It would be able to form carbon dioxide, right? If it gets oxidized. So if it is getting oxidized, it is forming carbon dioxide. So it would definitely get oxidized. And in the process, it would be reducing the metal to iron. So guys, do you understand what is happening in this entire reaction? Why is it a so famous industrial method? This is my initial reagent, right? I have reacted with water. I got these two products. This is what I need. I don't need Fe3O4. Now see what is Lane doing over here. He is regenerating this iron by reacting with this water gas. So guys, that means you just buy iron for one time and the reaction will keep on happening in a cyclic method. Did you understand how much money is he saving right now? And that also what is he using? Only water gas, means only coal and steam. You can understand how cost efficient this method is going to be now. Okay, that's why it's the industrial. Yeah, definitely with it. So one more time, guys, what actually happens is it's a method which is being used for cyclic in a cyclic manner. So you react iron and water together, you get Fe3O4 and hydrogen. Hydrogen is something I need. Iron, Fe3O4, ferrospheric oxide, or redoxy. Ferrospheric oxide, I take it and I reduce it, and again I get the iron out of it. Now this iron can be reduced, can be used further for more reactions. So you can understand that we are recycling our products in order to make our reactor. Right,
Sir,
Dipesh?
when we react C with H2O and we get CO, then we can also react CO again with H2O to get CO2 and hydrogen, right?
Come again?
So here the product is one of the products is carbon monoxide that we can isolate and react again with the
Oh no,
steam.
no, no, no. It is one of the product is not carbon monoxide. I'm saying that you understood this one. That's Fe3O4 and H2 is the two products in there.
Sir, the below one, the carbon.
I'm coming there. I'm coming there. Coming there. These are the two products you understood.
Yes,
Now
sir.
I'm taking this product. I'm reacting with syngas. Now in here, I'm showing you how carbon monoxide and hydrogen separately reduces Fe3O4 into iron. Understanding this point?
Yes, sir. So I was talking about the production part. This
Okay.
carbon steam gives CO plus H2. The
Here, here,
yes,
here,
sir.
here.
Yes, sir. So
Oh, all right. Yeah.
I was saying that again we can react the carbon monoxide produced with the steam to get CO2 and water, H2, right?
Huh, definitely, definitely. Okay, guys, is that clear? This is what I'm doing now. Here I am breaking the reaction up. How COH2 is gonna make iron. I'm just breaking this up. Like how CO is reducing iron, how H2 is reducing, right? And Apatik, we don't do this reaction in the same process. We do it in a separate chamber. From there, we take the water gas and flow it in my product mixture. Just so that the backward approach doesn't happen, right? So after we get the iron and water, what do we do? So this iron can be reused, no? Reused in this process again to form more hydrogen out of it. Again, we'll be adding steam. Again, we'll be generating. Yes, Pratish.
Sir, C plus H2O gives CO and H2. So we were needing H2, therefore the whole process is done. So we are getting H2 here also, right?
No, 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 no. You got me wrong here. This
Uh,
H2 is
it,
not a pure H2 that we need. Okay.
it is in the form of syngas, which cannot be separated.
It is in the form of syngas. You forget about this mechanism. That's right. You just think like some way we got this CORH.
Okay, sir.
Really. Those who are interested to know how do we get it, for that I have shown you that. That's that. Sir, can we turn CO2 in gas again? No, better. It's not like every reaction is reversible, right? So if you have to turn CO2 to syngas again, so you have to use a very strong reducing agent in order to do that. But no, it's not a reversible process. It's a one-digit reduction reaction. General. Okay. All right, guys. Moving forward. Now, after 10 more minutes, I'm going to give you a short break as well. Right. Now, have a look here. So, guys, how we are learning about how to produce hydrogens through different methods over here. Right. Now, Arham, first we have learned the basic method of forming hydrogen. which is in the industrial areas, the way we make it in the industries actually. Now here in the lab, we can make hydrogen in so many different methods, and all the reactions are pretty much known to you. As you can see that these two reactions is something that we have recently completed, recently done over here. Like when zinc and aluminum, when they are reacted with any bases, only metals in with any particular basis, you get sodium zincate, sodium aluminate, and the hydrogen gases. These reactions were there in your grade 10, if you remember, right? So here you are getting sodium zincate. The earlier one was sodium aluminate. This is sodium zincate. Here also you can see sodium aluminate is getting formed. Exactly, right? So this is the basis. So zinc and aluminum is acting like an acid, right after them, exactly. So it's an acid-base reaction, so you get salt over here. All right. Now, like the way I have just shown you through the bases, we can turn it. Similarly, with the help of acids also, we can make hydrogen gas. Now, how do you do that? Again, guys, this reaction was also there in your grade 10. When you react any metal with any acids, you get hydrogen gases, right? Now, I would like to ask you to focus on the second step. Guys, do you remember learning this in grade 10 that this is one of the method that earlier we used to use this method for hydrogen gas preparation. It was there in your grade 10, if you remember this. So when zinc is reacted with dilute sulfuric acid in the wolf bottle, we get ZnSO4 and hydrogen gas. This is one of the reactions that also gives high percentage of hydrogen as product. So earlier, guys, before we had Lens method or Bosch method I'm gonna teach you. Before we had this Bosch and Lens method, this is the method we used to use in the industries as well. In the lab, if you have to make hydrogen tape, this is the method that you're going to use. This is right now as well. We use this method to form hydrogen gas in the labs. I'm mentioning these things, guys, because they have never really asked before, but they might ask me this question: in which of the following method is the best for laboratory preparation of hydrogen or best for industrial preparation for hydrogen? They've never given this question before, but if they did, you should be knowing this as well, right? We have to be ready for every single situation. Now, guys, why is it dilute? Okay, I'll be looking at the doubts in a minute, guys. Why is it dilute, not concentrated? That's the first question. Second question is, why is it sulfuric acid? It can be any other acid as well that we can use in the lab, isn't it, guys? Because you learned in grade 10 that when metal is reacting with acid, it gives you hydrogen gas. So it can be any acid we could have been using there. So why is it only H2SO4? Now here I'm writing that why don't we use concentrated H2SO4? So let's talk about why not concentrated, and then we talk about why only H2SO4 is being used. Now, first thing is, why don't you use concentrated H2SO4? Guys, always remember this. Concentrated H2SO4, this concentrated format of it, it's a very good oxidizer. Now, what do I mean by that? And how is it oxidized? First, guys, when you heat concentrated H2SO4 up, it would form H2O, SO2, and I guess you know him, nascent oxygen, isn't it? Now, guys, you know that nascent oxygen is something like nascent hydrogen is a very reactive element. Nascent oxygen is also a very reactive element. Nascent hydrogen is a very good reducing agent. So nascent oxygen would be a very good oxidizing agent. Common sense, guys, we are not learning anything. It's all the things that we have already acquired is in grade 10 only, right? These kind of knowledge. Now, you can understand if I react concentrated H2SO4 with it, then what would be the problem? I would be getting ZnSO4, that's not my problem. But the hydrogen gas would immediately react with the nascent oxygen to become water. And water is not something that I want, right? I want hydrogen gas. So that's why I cannot use concentrated sulfuric acid. Right, Sayed? Right, Ritik? Clear? Clear, Pratham? Now, why are we using sulfuric acid? We could have used nitric acid. But guys, nitric acid, even in its normal state, it breaks into H2O, NO2, and mesotroph. Nitric acid is a famously known oxidizing agent. In organic chemistry, I'm gonna teach you this many times that we would be giving nitric acid, and instead of getting a nitrated product, we get an oxidized product. Okay, so it's very infamous for this particular reason. So again, we'll be getting water out. So that's why, guys, we avoid all the other kinds of acids and we only focus on H2SO4 and on a dilute basis. Okay, so that's the entire logic. Now, so what have we learned so far, guys? So right now we were learning the different methods of forming hydrogen. We learned, first of all, we learned the industrial. This first method is something which was very simple, guys. Metal with water gives you hydrogen. This is not something from where you can expect questions coming in. Lins process is something important. After that, guys, we learned how the metal and bases can give you hydrogen. Then how a metal and acid can give you hydrogen. Right now, electrolysis. Through electrolysis, how do we form hydrogen? Again, guys, this was there in grade 10. Remember, in grade 10, you learned electrolysis of water, right? The first time you learned about electrolysis, guys, it was electrolysis of water. So when you take water and when you have to give a little bit of acid on it, guys, because water is a covalent species. It doesn't break electrolyte. It doesn't break, right? That easily. That's why with it, what do? We add a little bit of acid, right? In order to drops of H2SO4. Remember learning in grade 10. So over here, Binali, what would happen if you react them together? And if you put them under cathodes and anodes, then what would happen here? The water would break into H plus and OH minus as usual. Now, who would go to cathode, guys? Cation would go to cathode. So in the cathode, what would happen? The two molecules of hydrogen, two atoms of H plus ion would go, and it would take two electrons and become hydrogen. Very good, Pratham. And in anode, what would happen, guys? 4 OH minus would go. They would release 4 electrons and they would make two molecules of water. And so in the cathode, we get hydrogen gas. In the anode, we get oxygen gas. This particular reaction is important, guys, because you can clearly understand it's not a normal, straightforward reaction, right? How the oxygen gas is formed, it is getting formed from OH minus. So you need to know the method. Yeah, guys. Haritri, Rizwan, all clear? Ashwin, Rahul? Great. Now, guys, we learn the next method, which is the Bosch process. Now, in Bosch process, what we do, guys? First, again, guys, this is also using the water gas here. Okay, that's just like the Lens process. So I'm writing over here, water gas is passed through a catalytic mixture of Fe2O3 and Ya2O3. You have seen this molecule before as well in hydrocarbon. In which reaction? Fe2O3 and Cr2O3 mixture. Where have you seen this? No, not controlled oxidation. Very good. Apratim and Devi. Anybody else? Right answer, Anish? Apratim. I've taken your name on three. Anybody else, guys? In hydrocarbons, this particular reagent is being used. Very good, Samya. It is being used in aromatization. Yes. Aromatization. Okay. In aromatization reaction, we have been using this reagent. Now, there, guys, why did we use this reagent? Just one sec. Why did we use this reagent, guys? The major reason was in there, if you remember, we were turning N-hexane to benzene, right? What was the N-hexane here? This. What is benzene here? Correct. Now, this to this is nothing but oxidation. Oxidation because you are decreasing the hydrogens. So that means, guys, it is a very good oxidizing agent. Is that clear for all of us? Right? If it's a very good oxidizing agent, guys, how is it going to help us now? Now have a look. When carbon and water are mixed together, this is getting CO and H2. I have shown this reaction before as well, right, guys? This is the way you form water gas. Okay, this method has a name. The name of this method is coal gasification. Gasification. This water is not liquid water, guys. It is steam. Correct? It's called coal gasification. When you use this mixture of CO and H2, this water gas mixture, with Fe2O3 and Cr2O3. Just 1 second, guys. Okay. Oh, wait. CO and H2. With Fe2O3 and chromium. Fine. So it would get converted into carbon dioxide. Just 1 second, guys. It will form the water, and then we'll be turning into induction process. Okay, now have a look, guys. First, we'd be taking this water gas here, and then we'd be passing it through the Fe2O3 and Cr2O3 mixture here. Now, it being an oxidizing agent, what would it do, guys? It would oxidize the carbon. This is syn gas. I mean, sorry, yeah, this is syn gas, so not water. Synthesis gas, right? Syn gas is what we call it. Anyways, the same thing, they are not different at all. So CO and H2 is what you have. Now this mixture, if you take it through the Fe2O3 and Cr2O3 mixture, what would happen is you will form carbon dioxide and water, right? Because both of them would get oxidized. Now, in this particular process, the water that you get, if you selectively reduce in presence of iron metal, what would you get, guys, over here? You'd get hydrogen and Fe. That is. All right. This is in the form of steam is what you get. No? So you'd get hydrogen gas from there and Fe2O3 back here. Now, this is called the Bosch process. Now, guys, so that there are two processes of formation of hydrogen. One is Bosch and one is steam. Now, if somebody asks you which method is comparatively more useful or more, efficient method, so definitely, guys, you'll be talking about the Lane's process, because over there, exactly, over there, you have seen that the byproducts has been used to make the initial products as initial reactants as. So definitely, that is going to be our more efficient method of formation of hydrogen. So in the industrial method, Lane's process is the most used industrial method to form hydrogen gases. And in the laboratory method, zinc and H2SO4 is our dilute H2SO4 is the most efficient method of formation of hydrogen gas. That's all about the formation. Now, guys, take a 5 minute break. After you come back, we'll be talking about hydrides, different types of hydrides there, and the last part of this chapter where we are going to talk about the hardness of water. Okay, can we not combine, or we still have two of it? Guys, you can go for a break. Those who have doubts, you can stay back. Can we not combine both of them because we still have Fe2O3? No, better. Actually, no, it's not like just a combination. It's not like the Fe2O3 and Cr2O3, we just mix them together. Whenever you are talking about organic mixture as well, no, we have to mix it in a proper method. Like there is a proper molecular ratio over there as well. We cannot just give any amount of Fe2O3 and any amount of Cr2O3 in there, right? So the product, like I said, in every single reaction, the product that you get They are not pure. The first Fe2O3 is a pure form. This Fe2O3 is with impurities in it. So you cannot use it as a reagent again, right? If it was pure, then you could have used it, all right? Swaraj, try to understand that why is the ortho product increase, ortho hydrogen amount increasing? Clearly, because when you are increasing the temperature, you are giving more and more kinetic energies to the systems, right? Now, when you give more and more energies to the system, let's say this is where my ortho hydrogen is, and the para-hydrogen is more stable, ortho-hydrogen, let's say in this form. So when you give more and more energy, you are increasing the energy of the hydrogen molecule. So it would be coming more and more to the ortho-hydrogen. No? Ortho-hydrogen is in the higher energy state. Para is in the lower energy state. So when your temperature is less, you get more of a para. When your temperature is going higher up, you are getting converted into ortho. Right? Right. Yes, sir. Mehak?
So technically, you're right that para-hydrogen should be more stable, but I
Mhm.
was going through the module and there it said that ortho-hydrogen was more stable. So
Ortho-hydrogen is more stable and more abundant. What is it
more
written?
stable.
In which module you are saying?
So
In
the
the grade
askIITians
11 one,
module.
grade 11 one.
Yes, sir.
You can send me a picture of it. I would definitely look into this.
Sure,
But
sure.
don't worry about it. Para is more stable in between hydrogens. Okay,
Okay, sir.
because of the you can clearly see that the magnetic property. Yeah, exactly. And again, better there is. Acha, wait a second. They are saying ortho is more stable. When they are saying that, that means they are considering at the room temperature. Maybe they are not mentioning that. When when they are saying that ortho is more stable, maybe they meant in the room temperature ortho is more stable. Have they noticed mentioned anything like that?
No, sir. They didn't mention the temperature. But they only mentioned that the pure form can be of para can be obtained at 20 Kelvin, but the pure form of ortho cannot be obtained.
20 Kelvin.
Yeah.
Hmm.
Pure para can be obtained at
Means at the
20
lower
Kelvin.
temperature, na?
Yeah. And then, but pure ortho can never be obtained. That's
Pure
all.
because the ortho is only possible when you're increasing the temperature. There you get a mixture of para and ortho always. But when you decrease down the temperature, you don't have ortho, you have only para in there, right? So that gives you the entire idea about it. No, when you're decreasing the temperature, the kind of hydrogen that you're getting, that is definitely the more stable one. From there
Yes, sir.
on.
I think it's a printing mistake because all the other facts are
No,
correct.
maybe they wanted to tell you at room temperature para ortho is positive, which I have mentioned the percentage as well, right? 3:1.
Okay, sir.
That can possibly be the BC5 address. Okay, sir, could you once again explain? The rest of you can go for a break and come back, guys. So could you once again explain why the concentrated H2O doesn't use? So actually the point was what I said, when you use the concentrated H2SO4, now concentrated H2SO4 acts like an oxidizing agent as well, just like nitric acid. So it would make the hydrogen turn into, that's why we don't use it. All right?
Got it, sir.
All right, yeah. Okay, guys, don't worry. If you have any more doubts, we'll be discussing about that right after the session as well. Okay? Take a break and come back in 2 minutes. Then we can discuss. Right, guys, come back now. Back quickly and turn on your cameras. Quick, guys. Mikhail, Ashwin, Arnav, quickly, beta. Okay. Now, guys, we talk about the hydrides here. Okay. So far, before I get started with the second half of the webinar, guys, so far, I guess if I, yeah, I am looking at the chats, not the YouTube ones here. I'm going to. Like I was saying now, guys. Like I was saying now, guys. Just 1 second. Mm-hmm. Now, all right. Now, like I was saying over here, guys, that when you talk about I mean, when you talk about the hydrides, there are total two types of hydrides, actually three types of hydrides. And if you just notice, before also we have talked about this different types of hydrides. Those who are watching live now, they can send their doubts in the live chat of YouTube as well. I am active in there now. So now, like over here, guys, what actually happens is the first half of the chapter, if you notice, all the topics are very like I can understand in a one session you are learning that might be the reason why you might feel a little bit of saturated. But if you look at the first segment of the chapter, 90%, not 90%, but 70% of the topics were kind of known to you. You have seen it once or twice in different grades as well, right? Now, this part of the chapter is something that would be a little bit new to you, and most likely the questions are going to come from here. All right. So, guys, for the next 45 minutes, you stay with me because I'm going to talk about two important pocket regions of this chapters, of this particular chapter. First is the hydride. One of the pocket regions of this topic is, guys, how many types of hydrides are there? One is ionic hydride, which is also known as saline hydride. I told you in the beginning. The next one is we have covalent or molecular hydride, and the third one over here is we have interstitial hydrides as well. Interstitial hydrides as well. These are the three types of hydrides that we have here. Okay. Now, if you talk about the first one, which is the saline hydrides or the ionic hydrides, you can understand when we are taking group 1 or group 2 metals and we are combining them with hydrogen, we get the hydride like this: sodium hydride, magnesium hydride, calcium hydride, right? These are actually called the ionic hydrides, saline hydrides, correct? Now, guys, when you know like somebody's ionic in nature, you can clearly understand they would be showing properties like ionic compounds as well, correct? Now, here, as you can see, that all the properties that I'm writing over here, they are all the properties of ionic compounds, isn't it? They are crystalline solid, right, Ashita? This is for ionic compounds. We have seen them making crystalline solids. They have high boiling and melting point for every single ionic compound. We have seen this kind of thing happening. Conductivity is high in their liquid state. Again, ionic compounds are gonna be like that for sure, right? Then again, if you look at, they release hydrogen gas at the cathode. This is something I mentioned, right, guys? They are, sorry, it is gonna be in the anode. They release hydrogen gas at the anode, right? H minus is something that you form from there. So the hydrogen gas will be formed in the anode segment, right? Now, they act as reducing agent. Clearly, guys, you know that if you are talking about metallic hydrides, so definitely they would be acting like reducing agent because all the kinds of hydrides are reducing in nature. Now, in grade 12, I'm going to talk about two hydrides, those who are the most highest reducing agents out there. Okay. So the highest reducing agents in grade 12 that I'm going to talk about is lithium aluminum hydride and sodium boron hydride. Guys, these are the two reagents I'm going to flood you with in the grade 12 organic chemistry. There are a lot of things that these two people are going to do in organic chemistry going forward. Okay, they are very strong reducing agents out there. Now, let's talk about the thermal stability. Now, guys, what is thermal stability? By the way, this question can come in different methods, different compounds as well. Over here, Pratham, let's say they are asking you a question of thermal stability. All you have to understand is, wasn't NaBH4 used for oxymercuration? Very good, Sean. It is being used in the demercuration scale, not in the oxymercuration, isn't it? Now, right. Now here, if you see, what do you mean by stability in thermal stability? What do I mean by that? That means when you give temperature, when you give heat, how stable the molecule is. That means, guys, we are talking about bond strength here, right? If Anish, if the molecule is very strong, then it would be holding up even in high temperature. Otherwise, for us, definitely it's gonna break down. So exactly, exactly in the demercuration state of process, correct. In there, we use the NaBH. Now, here if you see what the about the thermal stability in here, yes, it's exactly like when you have high bond energy, when you have high stability of bond, then your thermal energy would be highest. See, if I talk about lithium hydride, it is the most stable molecule according to the statement over here. Now, why is that? Try to understand, guys. If I talk about lithium, sodium, potassium, rubidium, what am I doing? I'm increasing the size, isn't it? As I'm increasing the size, then what would happen? The lattice energy would decrease. No, beta, there is no orbital mismatching in ionic compounds. Ionic compounds doesn't go for orbital matching, right? It is for covalent compounds. For ionic compound, we call them lattice energy. What is lattice energy? It's the ionic energy, if I say. You can clearly understand a small atom with a positive charge would be more dense than a atom this big with one positive charge. Where do I have more charge density, guys? Definitely in lithium, right? Because of that, exactly. As I have more charge density, my molecule would be binding strongly with H minus. Correct? So that's why
For
it is.
monoatomic ions, we check with the lattice energy, and for polyatomic, we check with the polarization power.
So for monoatomic as well, we look for the polarization.
No,
But
so like if you have the polyatomic ones, then we would have to look at the covalent character. Once with
exactly, like the Fajan student, right? Now, so guys, you go for
yes,
high lattice
that's why
enthalpy
like LiH is very thermally stable, but LiCO3 is not. That's Li2CO3 is very unstable.
because it breaks into Li2 and CO2, and Li2O is as a
Yes.
product. Correct. Yes. Anyway, very good. Now, guys, let's come to the next point. Okay, the answer to this question is gonna be high lattice enthalpy. Okay, guys, high lattice enthalpy of LiH and low lattice enthalpy of RBH. The reason is charge density. Okay, you can also use this terminology as well, guys. Charge density. So the charge density is high in lithium. Here the charge density is high. Here the charge density is. In this way also you can explain this thing. Now, hydrides of lithium, beryllium, magnesium has significant covalent character. Like a moment before only we were discussing that there is something called Pajan's rule, right? And the Pajan's rule tells you that when you have high polarizing power, you have high covalence. Now, what is this polarizing power? Polarizing power is something that depends on charge density. So, high polarizing power means high charge density. When you have high charge density, you are definitely going to be more polarized. If you have more polarizing power, then you'll be more covalent in nature, right? If I talk about lithium, beryllium, magnesium, these are the elements, those who are in the top of the periodic table in the groups. If I talk about where is lithium, lithium is in group 1. First element is lithium. Forget about hydrogen, guys. Here in group 2, we have beryllium and magnesium. Now, why am I taking magnesium? Beryllium is the first element. Now, why am I taking magnesium? So guys, you learned in periodic properties something called diagonal relationship. So the properties of lithium and the properties of beryllium would be kind of similar, right? So that's why these people, as they have small size, as they have small size, because of that, so due to they have small size, they would be having high polarizing power. Polarizing power. If they have high polarizing power, then what would happen? They would be having covalency generated in their ionic compounds. They'd be having polarizing covalency getting generated in their ionic. This is something you learned back then in grade 11 chemical bonding chapter, right? Now, let's go for the covalent hydrides over here. What is the covalent hydride? So you can understand for metal hydrides, it is ionic because metal, non-metal is ionic compound. For covalent hydrides, what do you have to do? Non-metal, non-metals is covalent hydride. Just like covalent compounds out there. This is the mega version of metals after 9 plus. Kind of effect. So just like covalent compound guys, it is showing the similar kind of properties. Soft, less boiling point, less melting point, poor conductor of electricity, and all the hydrides are reducing agent anyway, so don't need to say anything about that. So what all the covalent hydrides are we talking about guys? We are talking about water. We are talking about ammonia. See, both of them are non-metals over here, right? We are talking about hydrogen sulfide and these kind of compounds. Now, these covalent hydrides are of three types, guys: electronically deficient, electronically precise, electronically rich. See, don't try to remember all these things. These are all that you already know. So if I ask you, you give me a particular molecular hydride which is electronically precise. Precise means that it has filled up its octet. So I want you to give me an octet configured hydride. So what would you say? You would go like, no beta, CH4, not water. Why is not water? Because water is an electron rich hydride. Because it has lone pair on the top. As it has lone pair, so it is electron rich. This is precise. Correct? Similarly, silicon hydride, SiH, precise. Water, ammonia, these are very good with it. These are electronically rich, right, Shubhangi? Right, Devash? Now, who are electronically deficient hydrides? Give it a go, guys. You have to give me element with hydrogen electronically deficient. Electrophiles, very good. Give me a name. Now, not ammonia. Very good. Many of you are right over here, guys. pH. Group 13 elements are electronically deficient. Always remember this. BCl3, BH3, boron compounds are always going to be here. pH. Now, guys, for BHC, I'm going to teach you a little bit more into details going in the next few minutes. Actually, what happens is now BH3 being electronically deficient, it doesn't stay like BH3. It forms a dimerized structure goes by the name of B2H6. That's why in hydroboration oxidation reaction, you have learned that B2H6, not BH3. Remember at that time I told you? Now, this particular bond is known as banana bonding. All these things are there in group 30, P block. It's called banana bonding. Hydrogen is making two bonds, right? C center two legs. I'm going to tell you about this in details going on. Okay, so these are the three types of them. Now, metallic hydride is something, guys, that is going to be new to you for the time being. This particular topic is there even in your boards as well, guys, in this particular year. This year means I'm considering you are all in grade 12, right? You have to worry about that. I guess no one is repeating grade 11, right? So, considering all of you are in grade 12, guys, this is something that you're going to learn one more time. So, give it that much of importance. D and F block. In there also you are going to learn about metallic hydrides, but in here in DNA block you are going to learn as interstitial hydrides. This is the name by which you are going to learn that in grade 12. Okay, so if you guys here, I want your attention now. See, all the hydrides that I have taught you so far, They are all called stoichiometric compounds. What do we call them? Like covalent and ionic. Together, we call them stoichiometric compounds. Stoichiometric hydrides. What do we mean by stoichiometric hydrides, guys? That means, exactly. Relating to the valencies. That means you are going to use them in whole numbers. Okay. You have seen that in every situation, I have either one hydrogen or two hydrogens. Just the way the valence is supposed to be. But if you look at this particular compound, metallic hydrides, you can clearly see that these are also called Barthelor's compounds, guys, or we can also call it non-stoichiometric compounds. We can also call them non-stoichiometric hydrides. Now, what is that? If you look in here, the compounds are having titanium hydride is 1.8, vanadium is 0.56, lanthanum hydrogen is 2.8 lanthanum hydrides. So you can clearly understand who are making this kind of hydrides, guys. D and F block elements. That's why we are going to repeat in the D and F block chapters as well. Correct? Now, can every D and F block elements make this kind of hydrides? The answer is no. The D5 to D7. D5 to D7. What do I mean by D5 to D7? Means I'm talking about the electronic configuration. I'm talking about manganese right now. How does the manganese electronic configuration go like? 3d5 4s2, right? This is your d5. This is what I mean here. Okay, in original state who has 5 electrons in the d structure. So I'm talking about manganese means I'm talking about group 5, group 6, and group 7. These are the groups I'm talking about, guys. D5, D6, D7 means I'm talking about group 5, group 6, group 7. Means manganese, iron, and cobalt. Okay. In these three groups, that means manganese, technetium, rhenium, iron, ruthenium, osmium. This is just one second. Iron, right only. Cobalt, rhodium, iridium. Okay, these people cannot form hydride. That's why we call what we call it. We call them hydride pores. Okay, we call them hydride pores as well. For these particular three series, we don't see hydrides for them, so that's why we call them hydride pores. Okay. Now, other than that, guys, as you can see, they are formed by P or F block elements. Then you have these elements not forming them. They have metallic character. They are brittle in nature, and the composition might change. Now, guys, what is the reason behind this kind of compounds getting formed? Non-stoichiometric compound getting formed in here. So the reason behind this, there has been two reasons that they have mentioned in the NCRT. One of the reason is something that was being taught in one of the chapters that used to be there in grade 12 in the last year, goes by the name of solid state. Okay, exactly, stoichiometric defects. So in solid state chapter, guys, anyway, you have to learn it for your J advanced preparation. In solid state, you are going to learn this. Whenever a lattice, a crystal lattice is being formed, you can see that here in this particular picture. Whenever a crystal lattice is being formed, just one second. Yeah. A crystal structure is being formed, like here, the hydrogens being very, very small in size, while the crystalline structure is getting formed, they might be found or place themselves in the interstitial sites. This is called interstitial sites. Okay, when the lattice is being formed, the gap that is there in the lattice, the hydrogens might fit in there and get connected in the interstitial sites. So because of that, so they are acting like an impurity here. They are not compounds. These hydrogens are acting like impurities in this metal structure. In this situation, we will get this interstitial compounds. All right. This is the logic that has been mentioned in the, about this. So guys, again, it goes like, because the hydrogen, when it is like the metals lattices, when they are getting formed, the hydrogens are getting entrapped in the interstitial spaces, and that's why, guys, they are also called interstitial hydrogens. I've told you that, right? They're also called interstitial hydrogens because they are entrapped in the interstitial spaces. Okay, so that is the logic there. Yes. Okay. Like I was saying, the interstitial gaps alone. Okay. Now, guys, there is another type of hydride which has been there, called polymeric hydride. It is not a clear, it doesn't come under any clear segregation of hydrides. It's just an additional information about hydrides, which is there are types of hydrides known as polymeric hydrides, where the hydrides are actually making polymeric structures. This is being taught in S and P blocks, specifically in S block. In S block, it is being actually taught that they form long chain compounds. As you can see, beryllium is forming a kind of a chain-like structure here, right? So this is in the solid state. In the solid state, beryllium forms chain-like species, like you can see. Aluminium and can also do that kind of thing. AlH. Do you understand how the species is being formed? These three, this is the aluminium AlH. This is another AlH. Now they're combining like this. If I have to give them some color, this is the two LH2s. They combine together and form polymeric structure like that. Okay. In the solid state, not in the other state. When you increase the temperature, the bond starts breaking. In the liquid state, it's not a polymer anymore. It becomes dimer. In gaseous state, it's a monomer. Yes, Pratish, you want to say something?
Yes, sir. Sir, this structure is forming due to banana bonding, right?
No. For boron, it was banana bonding. For these people, it's not banana bonding. When
Sir, like
you
Al, it is 6 electrons in total. It is combining with ALH
okay,
when
okay,
it's forming an ALH3.
okay, I got your point. I got your point. So you're talking about this L, na?
Yes, sir. So it is
This L.
deficient of 2 electrons.
Huh.
Sir, so isn't it forming like a banana bond like structure?
See, actually, the point of banana bonding is actually found in boron because of a reason, actually. See, banana bonding has a little bit more to discuss about. There, it's a kind of a situation which is getting formed because of you can see there are three centers present in there, right? And the electrons are actually coping up with all the three centers, but there are only two electrons that is there, right? Now, if you look into this kind of situation, it's not really the kind of the way I have shown you this particular structures. They, it's just a way of representing. Okay, 1 second. This is just a way of representing. The reality is, you, like I said, you get this kind of structure when you are making a solid structure, right? So, see, you can call this as a three-center two-electron bonding as well, but it's nothing but a packing kind of a structure. It's not really like if I talk about BH3, okay, B2H6. B2H6 is found in all the different states, but that is not happening for these. Over here in these few peoples, what we see is you get to see these kind of structures only in solid state. That means it is nothing but this is nothing but a packing kind of a structure. So we never call these structures as banana bonding.
Sir, like the specific reason for this is isn't it like the H is not having a lone pair, therefore it is not a banana bond.
Yeah, come again. I was just distracted a little bit. Come again.
Sir, H is not having a lone pair. There is it like because of that we are not calling it a banana bond.
No, beta. If it had a lone pair, we would have been calling it normal coordinate covalent bonding. It doesn't have a lone pair. That's why we generally call it a banana bonding. Okay, let's do one thing. Let's talk about this banana bonding, right? Just wait after the session once. Then I'm gonna tell you about the entirety of it. Okay.
Okay, sir.
Right. Right now, let me just complete these step topics real quick. Now, guys, um, here we are going to talk about different compounds of hydrogen. Now we are towards the end now. It's not going to take long. So we're going to talk about different compounds of hydrogen. So first we're going to talk about water, and then we are going to talk about hydrogen peroxide. Okay. First, guys, for water, as you know, it is having a hexagonal structure when it is in the solid state. In the crystalline solid state, it is forming an hexagonal structure. Like how it is forming this hexagonal structure? Because you know, in solid state, it is capable of making hydrogen bondings, right? So in this way, it makes specific kinds of hydrogen bonding to make a hexagonal, like benzene ring kind of a structure, right? The next one is in 3D, each oxygen atom surrounded by 4 hydrogen atoms, tetrahedral. So now, guys, this is something very important. The structure might look like hexagon. The structure combining together looks like hexagon. But if you look for one oxygen in this hexagon, it is surrounded by 4 hydrogen atoms. How? See, let's draw one oxygen here, hydrogen, hydrogen. These are the 2 hydrogens. Now, what are the rest 2 hydrogens? They are here forming the hydrogen bonding. So, if I talk about one particular oxygen, it is combined by 4 hydrogens, surrounded by 4 hydrogen atoms. So, it's a tetrahedral structure that they make with these 4 hydrogen. That's what they're practicing. Okay. The overall structure looks like hexagon, but one oxygen is tetrahedral surrounded by the. Understood? Now, just 1 second. Let me look at the YouTube one as well. Perfect. So now, what all chemical reactions are there? So we're doing 2 liters of a tetrahedral structure of hydrogen surrounded by hydrogen oxygens every day. Right. You. Okay. When we talk about the kind of reactions that water is capable of doing, guys, one of the thing is water can act like both acid and base, which is also known as autoprotolysis of water. Just guys, excuse me for 1 second, okay? Coming back. Right. So now, like I was saying here, that's all. So when two waters are both acid and base. So as we can see here, it is called autoprotolysis of water, where one water molecule is taking the hydrogen from the other, and the OH minus is getting from. So here, one water molecule is acting like a base. This is base because it is taking the hydrogen. Another water molecule is releasing the hydrogen. So it's an acid, right? So this is one of the property that water is capable of. You learned this back then when you were learning the pH. Remember, in there also I have taught you this autoprotolysis of water state, right? Now, guys, reactions with metal is just going to be a repetition. Amphoteric also you can exactly. It's just going to be the repetition segment, guys, right? How hydrogen gas is getting formed when they react, the metals react with the water. I'm not teaching you this anymore. Reaction with non-metal also. So here, guys, you can understand when carbon and water is reacting together. This is something also I have taught you here. We get the syn gas produced from here. So this is one of the reaction. Reaction with fluorine. So what actually happens is when you react fluorine with water, you get hydrogen fluoride, and it's a very simple reaction, which is kind of a displacement kind of reaction, guys, that water breaks into H plus and OH minus here. And then it's a stage forward, the H plus reacts with the fluorine and it gives you the HF molecule. So this is the second reaction. Reaction with chlorine, you can clearly understand the similar way. When chlorine and water, when they are reacted together, you get HCl and OH. Later on in guys, I'm gonna tell you that these reactions that I am showing you here, they are not at all that stable. These products are not at all that stable. They are gonna rather form some kind of acid, like here it is gonna form HOCl, hypochlorous acid. And similarly, here also, you are gonna get these kind of acids getting formed here, rather than HF and OH minus, HCl and OH minus. Okay. But still, if you open up the NCRT, this is the reactions that they are giving. So that's why we're going to stick to that right now. Okay. Again, guys, don't focus on the reactions. These reactions are needed for your J advanced preparation and stuff, but still don't need to worry. No need to worry about remembering these reactions, because the moment you see them, just apply your common sense and you'll be able to find them. Now here, again, guys, reaction with metals and non-metals with non-metals oxide. I'm not audible. Am I audible or am I not? I am. I am now. Okay, great.
Sir, you are audible.
Okay, guys, great. Now, guys, reactions of water with metal and non-metal oxide. So you know now, when you react it with metal oxide, you get base, and when you react it with non-metal oxide, you get acids. All right. So that is why when I'm reacting with Na2, I'm getting NaOH, which is a base. But when I'm reacting with any types of non-metals, we are getting these acids. But still, guys, have a look in these reactions, because see, Cl2O7 is the oxide of chlorine, gives you HClO4, perchloric acid, right? So these are the names that you have to practice a little bit. SO2 gives you H2SO3 and H2SO4, these are simple, right? N2O5 gives you HNO3, P2O5 gives you H3PO4, these are simple, right? But still, you just have to go through it for once. SO2, we can say that nucleophilic attack on H2 on sulfur. Yeah, definitely. Okay. That's the mechanism that we can definitely. So, guys, in a nutshell, you can say like, when you have metallic oxide, you know they are acidic in metallic oxides are basic in nature, right? So when you react it with water, you would be getting some sort of base. And similarly, when you have non-metallic oxide, when you react it with water, you'll be getting acids. That's it. Okay. Now, so guys, this is the second pocket region of this chapter. So the entire chapter is not important. There's only some certain points from where you get to see the question. One of the point was definitely that I've been teaching you before, that the preparation of hydrogen, Bosch process, Green's process, and all these things. Then the other one is this one. This is the hardness of water. So this part is something from where we have very much noticeably the questions have been given in JEE Mains. So here, guys, what is hardness of water? So there are two types of water out there. One is called hard water, the other one is called soft water. Right. Now, hard water doesn't mean that you're gonna throw it in the floor and the floor is gonna make it crack. It's not gonna be like that. Hard water means you're gonna have some particular salts which is present in that water. Now, the salts are actually of calcium and magnesium. Now, why do we call them hard water? Because see, this kind of water, they are not used for either drinking, or you cannot use them for your daily activities as well. Exactly. They don't form that, if you just you have learned this in grade 10 as well. Yeah, they don't form that leather or scum when you actually, yeah, the foam thing, exactly. When you add some, what do you call it, detergent or something on it, you don't get any uh, lather. Like in Hindi, we don't get jhag. Okay, simple. So What is this hard water containing over here? That's the bubbles, whatever it is, whatever it is, right? So here, what kind of waters are known as the hard water? As you can see here, when you have calcium and magnesium salts in your water. Now, what kind of salt? It can be bicarbonate, it can be carbonates, it can be sulfates, it can be chlorides. Any kind of salt of calcium and magnesium would give you the hard water. Only sulfates better. Okay, bicarbonate, sulfates, carbonates, and chlorides. These four. Okay. Now, what happens when actually, like, how are they not showing you those lather or like bubbles or whatever you are calling that? Why is it unable to show? So actually, what happens is when you are dissolving any detergent on it. Now, detergents are nothing but long fatty acid chains. As you can see here, this is soap. Soap is containing sodium salts of stearic acid, palmitic acid, and oleic acid. Right. So right now I have drawn the structure of sodium stearate. Guys, sodium stearate contains 17 carbons on it. If you have to write palmitate, it contains 15 carbons on it. Okay. So anyways, the sodium salt of palmitic acid or stearic acid or oleic acid is called soap. So as you can see, this is the structure of a soap. Now here, you can see this part is polar system. Correct. What actually happens is when you react with the calcium and magnesium salts of water, when they react the calcium and magnesium salts of water, they make calcium and magnesium salts of that particular acid. So earlier it was sodium stearate. Now with reacting with calcium, it would become calcium stearate or magnesium stearate. Now what would be the product of that? Because of this calcium and magnesium salt, they would form precipitate. Right? So the entire detergent you are putting in water, that would be the calcium is replacing sodium. So the entire detergent that you are putting in water, rather than using it this detergent to remove the dirty dirt from the shirts or stuff, it is getting precipitate, right? So that is why we don't form the leather or anything. Now there are two types of hardness of water. One is called temporary hardness, another one is called permanent hardness. Guys, I know that you are a bit tired, but this time I want your attention the most. Okay, so stay with me for the next 5 minutes. So there are temporary hardness, there are permanent hardness. Temporary hardness is when you have bicarbonates of calcium and magnesium. Permanent hardness is for the rest of it. Now, why do we call it temporary hardness? Because by just heating them, you can remove this particular type of hardness. When you take these bicarbonates and you just heat them, you get the carbonate salts and they precipitate downward. So after that, you just take the water out from and you'll be able to get the salt. Okay. But there's another method through which you can remove hardness, which is the Clark's method, where you are using these bicarbonates and reacting it with some sort of base. We generally use calcium hydroxide. Here also we get the calcium and magnesium carbonates. Anyways, the carbonate that we get, they precipitate down below, so we can remove them. Okay. Exactly, like I said, by heating them also definitely you can get calcium carbonate, carbon dioxide, and water. I'm not writing the byproducts because they are not needed. I'm just showing you how to remove this. Now, so I guess you can understand, guys, these methods are just heating or just some physical, it's very simple ways of removing the hardness. That's why we call them temporary hardness. So they are also not important. My important part starts from here, the permanent hardness. Now, guys, I want your entire attention for the next 5 minutes. Okay, this is the most important part of this entire chapter. See, there are three methods through which you can remove the permanent hardness. One is called permutate method. Okay. So also you can call it base permutate method. Generally, we call it permutate method. The other one is Calgon method, and then we have ion exchange resin method. All these three are very, very important. Let's start with the first one. Permanent can also be removed, then how it is permanent. Right? It is a little bit hard to work with it. So everything can be removed by chemical reactions, right? So for this, you can understand, you'll be able to see how much of efforts we have to put in here. But that was a good question actually. Anyway, what is this permuted method over here, guys? Nothing is permanent in life. Very good, Latik. So guys, what is the permuted method over here? So here you use a particular molecule which is called sodium hexametaphospate. Okay, just wait for a second. I guess sodium hexametaphospate is for Calgon method,
Yes, sir.
not for permuted. For permuted method, we use zeolites. We use zeolites. What are these zeolites? The zeolites are called aluminosilicates. They are called aluminosilicates. What is this aluminosilicates? Aluminosilicates are the kind of molecules, guys, which has aluminum and silicon compounds combined. Okay, I'm going to give you one of the examples of this. Na2 Si2, Na2Al2, Si2, or you can also call it NaAl Si. Okay. This is called aluminosilicate compounds. You can clearly see that this SiO4 systems are called silicates. With it, when you are using aluminum, then we call it aluminosilicate. Sodium over here is just used as a counter ion. So Na2Al2 Si2, this kind of compounds are sodium aluminosilicate. These are, in a short term, we call them zeolites. Now, how do they remove the permanent hardness from there? So what they can do is, these kind of aluminosilicates have a specific kind of structure which you can see in this particular picture. You can see they have a cage-like structure. And guys, this cage-like structure is very, very useful for them. What they actually do is, they kind of entrap the metal particles inside this cage. I don't know whether in this picture that is clearly visible or not. So as you can see over here, this is one zeolite structure. The zeolites, what they do is, they entrap the calcium metal ions inside the cavity of this cage. And they specifically take out the calcium metal from the entire solution. Guys, calcium and magnesium has different size. So that's why we cannot use the same zeolite to take them out. It's like we make it in a so precise manner that we can also control the size of the cavity. So for different metals, guys, we have different cavity size because their sizes are different. So we make different zeolites. Okay. Now anyway, coming to the things which is there now. See this Na2Al2Si2O8. This is one of the structure of zeolite, but it has been simplified to the form of Na2Zd. You can call the rest of the part as Zd. Zd for zeolites. Okay. Now what actually happens here? We take this Na2Z, not Zd. Z for zero. What do we do, guys? We give this Na2Z compound where we have the calcium or magnesium ion. What would they do? This Na2Z, like I said, this zeolite compound, this entraps the calcium, right? So instead of Na2Z, it becomes CaZ or NaZ. It's just like a displacement reaction. Okay? It's just like a displacement reaction, it just displaces the sodium from the zeolites. So I'm going to show you one small video in order to make you understand about it. Just watch this video now. But there is nothing to do with the reactivity in this kind of system. So like I said, it's all about the cavity size. So it's kind of, we make the zeolite cavity in such a way that it can take the calcium in the cavity. Okay, it kind of engulfs it. All right. We are trying to learn how to remove the calcium and magnesium ions from the hard water to make it soft water. Okay. So see, what are we doing? Here, I'm just taking you all the way up because they are trying to give you things in more detailed manner. So I'm going to show you here. See, what is happening here? So the hard water is being given. Now, you have the hard water in the bottom side over here, right? Calcium and magnesium chloride. Hard water contains different kinds of chloride or sulfide, right? Now, the water would first get deposited here. Now, from there, what would happen is the water would rise up. And the top part of this beaker contains the zeolite compounds. So they would react with the zeolites. And what would happen because of that? You can see that Na2Z and calcium chloride are reacting together and they are making CaZ and A. Right? So it's just like a normal displacement reaction through which we get the magnesium and calcium. Now, what would happen, guys? These calcium and magnesium zeolites, they are actually precipitated down. Okay, as you can see in the next part, you can see the calcium. So now the calcium and the magnesium zeolite has precipitated down. So the water on the top is just soft water. There is no calcium and magnesium. All right, it's just like a precipitation. Right, guys? So this is your one reaction. Now going to the next one. So the permuted method is being used with the zeolite system. You need to remember the structure of zeolite and this reaction that I have written in here. These are the all three things that you have to do for. Now let's go for the Calgon. Now Calgon is the next method. Again, this is also a very simple method, guys. In Calgon method, what happens is we are using a specific reagent called sodium hexametaphosphate. Sodium hexametaphosphate. Now, what happens in this process, guys? See, sodium hexametaphosphate looks like this. Na2. I'm going to tell you the reason behind this type of name as well. Na4. Okay. So what is being removed or added from hard water to make it soft? Ritik, like I said, the hard waters are the water that contains calcium and magnesium salts, right? So you have to remove this calcium and magnesium ions from with different processes, right? So that is what we have been doing for sure. So here the zeolites, they take out the calcium and magnesium from there, right? As a result, the water that is there, that is only soft water. No, beta, we're not adding hard water to calcium. Calcium is already there in the hard water. That's why they are hard. So when calcium and magnesium is there in the water, that's when we call it a hard water. Right? Our target is to remove the calcium and magnesium salts. So what are we doing? We are giving a sodium zeolite compound. It is reacting with the hard water that contains calcium and magnesium ions in it. And it makes calcium or magnesium zeolites. So now the water that I have that doesn't have the calcium and magnesium salts in it anymore. So do different zeolites have different cavity size also in the structure? Exactly, Arham. Do different zeolites have different structures, different shapes, and different cavities. So for sodium, the kind of zeolite that we are going to use, for calcium and magnesium, we cannot use the same zeolite. Zeolite structure will be different in use. All right, guys, 5 more minutes and we'll be done with this chapter. Okay. Now, Calgon. Calgon is called sodium hexametaphosphate. Now, why do we call it? First of all, guys, you can see this PO3 compound is called metaphosphate. How many of them are there? 6. So hexametaphosphate. And the counter ion is sodium. That's why it is sodium hexametaphosphate. Clear? Now we need to remember this particular structure for calculus. Okay, this is what they ask you the question. Now what would happen when you give the sodium hexametaphosphate in hard water? What contains in hard water, guys? The hard water contains calcium and magnesium salts in it. Correct. So what would this sodium hexametaphosphate do? It would again go for a substitution reaction with calcium and magnesium and form calcium hexametaphosphate. So Ca Na4. What just happened, guys? Two sodium got replaced by one calcium because sodium's valence is 1, calcium's valence is 2. For obvious reason. So as a result, Sean, we got a precipitate of calcium hexametaphosphate and sulfur. So I guess permutate and Calgon method looks the same to you. The only difference is the compound. Over there is zeolite, over here it is Calgon, right? Now coming to the last and the most important of all, which is called the ion exchange resistance. Ion exchange. Just watch this video, guys, and after that you are free to go. Here, if you see, just watch this video, okay? I'll be explaining this through the entire video. There is one additional topic that I have given in my notes. Okay, from there we haven't seen questions coming in, but still, guys, I have added up in my notes so that if you feel like you can go through it for your buffer region. There's nothing much to teach about that because it's just the normal reactions that we have been doing for water as well. I've kept it in my notes. You just give it a reading. I'm sure that you'll be able to understand that part. Okay, that's the hydrogen peroxide segment. I will tell you why it is. So, guys, first we are talking about ion exchange risk. So let me tell you what is this all about. You can see there are two systems given in here. One is called cation exchange resin and the other one is called anion exchange. All right. The first one that you see over here, this one is called cation exchange resin. Let me see. That's showing properly in the YouTube or not. The first one over here, let's just pause it for a second. The first one over here, the pink one, is called cation exchange. So guys, it has something to do with the cation that you can understand. And the blue one over here, it's my anion exchange. So what is happening over here? First, see what all things are present here. First of all, guys, you can see there's an inlet of hard water. The hard water is going to enter through the cation exchange resistance. You can see the name is also given, cation and anion. Now see what happens. Achha, there is something called dilute HCl and H2. So right now you just neglect it. Don't need it for the time being. I'm going to tell you what is it. Okay. Now guys, focus completely here. Now what happens? You can see now there's a common, this outlet of cation exchange regime is the inlet of anion exchange regime, isn't it? Correct. And there also, like here there were some acids, here there are some bases. I'm going to tell you the logic. Now, let the hard water flow through it. Now, what are they saying? Cation exchange regime is made up of carboxylic acid and sulfonic acids. And anion exchange regime would be formed by ammonium. Let me show you here. I guess they will be showing that as well. There is ammonium, RNA3. Okay. These are the two things that they are formed. Okay. So let's write it down here. Now I'm going to write down the reaction. So in the cation exchange regime, guys, I have the carboxylic acids substances. In the anion exchange regime, we have the ammonium's counter ion was OH minus in this particular way. Now, guys, what actually happens is when you pass the hard water through, the hard water contains calcium or magnesium in it. Focus now, guys. It contains calcium and magnesium. What would it do? The calcium would displace the hydrogen and make a salt with that particular carboxylate. So what would it make? RCOO whole to Ca or H. And what would it displace, guys? It would displace hydrogen. So what did you see right now? The cation got exchanged in this residue with H plus, right? So now I have H plus. In anion exchange residue, what happens? Let's say you have seen that, guys, that this is sulfate, chloride, and these kind of salts of calcium and magnesium, right? So you have, let's say, chloride or sulfates. What would they do? See, the compound in anion exchange resin was RNH3 NH3 plus. What would the Cl minus SO4 minus do? They would exchange themselves with the SO4 2. They would exchange themselves with the OH minus of NH. Now, what would be the product then? RNH3 here or RNH3 whole 2. And what would they get exchanged with? Correct. This would precipitate down. This would also precipitate down. So what would I have in my residual solution? In the residual solution, I'll be having H plus and H. That means, guys, I would be having water, right? This particular water is called deionized water because there is no other ions in it other than the H plus and H. Now let's watch the video. Now see, the calcium and magnesium salts are coming through the pipe to the cation exchange resin, right? Now there, what is happening? See, the cation calcium got exchanged by H plus on the top. Similarly, the same thing happens for magnesium as well. Now, guys, that thing is the precipitate, so that would precipitate down. Rest H plus, Cl minus, these two ions would be flowing through the pipe all the way as the inlet of anion exchange resin. Now, I show you here. This is for magnesium. If I show you here, these two anions like H plus, Cl minus, H plus, SO4 2 bar. These are gonna be in the filtrate because the rest of the two compounds are gonna be precipitated, right? They'll be precipitated down. Now these two would be the inlet of anion exchange. As you can see, this is the inlet of anion exchange, right? In there, the SO4 2 minus and the Cl minus, that would get exchanged by the NH3OH. The OH would be exchanging that Cl minus and SO4 2 minus. See the reaction now. The Cl minus and SO4 minus, they now form the compound and the OH minus is coming out. Correct? Now that compound is again a precipitate. So right now, in this particular outlet, guys, in this particular outlet down below here, in this outlet, what do I have? I have only H plus and OH, correct? Which is nothing but water, and we call them deionized water because there isn't any other ions. That's why we call it deionized water. They often ask what is the difference between distilled and deionized water. So this is going to be the distilled water can contain other ions in it, but deionized water cannot contain anything other than H plus. No, Ritik, how would it? There is only OH minus present in it, huh? As an anion. So as you can see, H plus and OH minus gives you. So these are the three methods through which deionized water is more pure. Yes, Raj, exactly. It's more pure And deionized water is something that we use in lab. We don't use distilled water in lab. We use deionized water in lab. In our lab, not in your labs. Your lab, I guess, in your school they are giving only distilled water. If they are using deionized water, then guys, it's a very good thing. Okay, you'll be getting very good results in all the. So Ritik is writing, we use tap water, sir, in lab. Same, really? Okay. So that's it, guys. That's all about this chapter. It was full of reagents, reactions, but guys, give it a go. They are not difficult at all. You have my word with it. And just go through this part. That's all you need for this chapter, hydrogen. Okay. Simple and this is a very simple chapter, and it's a very quick marks that you're gonna get from here. There is something that I'm adding in this part, guys. Okay. If you see the H2O, chemical properties of H2O. Okay. Hydrogen peroxide is a part from where you might expect a few questions, but no one has asked questions before this, guys. So that's why I have given this part of the note. Just go through this once. There are only physical and chemical properties present in it. I'm sure that you will be able to find it very easy because the things are very, very simple over here. Give it a reading and you will be running fine with it. Okay. There is one thing that I might have to teach you in the coming session where, guys, the problems regarding this particular chapter is there is one kind of question that is being asked, which you have also learned in basic concept of chemistry, which is this question: degree of hardness. You remember learning these questions in basic concept of chemistry, guys? How to figure out the degree of hardness in water? Yes or no? Or do you want me to give a quick revision of this? Okay. So guys, just give me 5 minutes for the revision of degree of hardness here. So what is the degree of hardness, guys? It's the amount of hardness present in water. Now, who are causing hardness, guys? Calcium and magnesium salts are causing hardness. So in a way, guys, we are trying to figure out how much calcium and magnesium salts are present in water, right? So simple question. But what actually happens is degree of hardness, like everything has a scale through which we figure it out. Let's say I'm talking about pH scale. pH is a scale, right? The acidity is being found with respect to pH scale. Similarly, guys, degree of hardness is also found with respect to a scale which is made by calcium carbonate. So just like acidity is found by pH scale, degree of hardness is found in calcium carbonate scale. Okay. So what you have to do is, let's say you have any compound of magnesium, or guys, just focus for the last 2 to 3 minutes. Let's say you have any compounds of magnesium or calcium present in your water. What you have to do is you have to convert it into calcium carbonate, and then only you can predict the hardness of water. Okay, let me tell you what do I mean. See, you can see there are some numbers that I'm writing over here. 162 grams of calcium bicarbonate is equals to 100 grams of calcium. 111 grams of calcium fluoride is equals to 100 grams of calcium.
So we can just
136.
find the moles of
Exactly.
calcium.
Exactly. So what is this numbers talking about? It's nothing but, guys, 1 mole of calcium bicarbonate is equivalent to 1 mole of calcium. That's what I'm talking. So whatever compound of calcium or magnesium that you have, guys, 1 mole of that is equivalent to 1 mole of calcium. I am just writing the molecular mass of those compounds. So how do you solve these questions? Let's see. Calculate the degree of hardness of sample of water, hard water. Is this using POAC? What is POAC? In the meantime, let's solve this question. Calculate the degree of hardness for the sample of hard water, which has been found to contain 36 milligram of magnesium sulfate per kg of. Now, guys, 36 milligrams of MgSO4 is what you, right? Now, 1 mole of MgSO4 is equivalent to 1 mole of calcium carbonate. 36 milligrams of MgSO4 means how many moles, guys? Figure out how many mole is it. So 36 into 10 to the power minus 3 grams divided by the molecular mass of MgSO4. What is it coming, guys? So magnesium is 24, sulfur is 32, 64. So 60, 120. Exactly. 120. So how many moles are there, guys? This many moles. These many moles of MgSO4 is equivalent. So exactly, no need to calculate it. Okay. This many moles of equivalent of MgSO4 is equivalent to 36 into 10 to the power minus 3 grams squared by 1.2 grams. These many moles of calcium carbonate. 1 mole of MgSO4 is equivalent to 1 mole of calcium carbonate. So these many calcium. So what is the value coming, guys? Calculate it and tell me. It's coming close to 3 into 0.3. 3 into 10 to the power minus 4 mole of calcium. Right? Now these many calcium carbonate means how many grams of calcium carbonate? So then you have to find out 3 into 10 to the power minus 4 into 100. Calcium. Calcium carbonate's mass is 100. That means 3 into 10 to the power minus 3 grams of. This is the hardness of. There is nothing that we are doing over here. First, we are finding out the number of moles of that particles that is equivalent to the similar amount of calcium carbonate. We are just converting into grams. This is the hardness of it. There is one particular information that you need to know here. When they are asking you about the hardness of water, they want it is always calculated in ppm, parts per million. That means in 10 to the power minus 6, how much is that? So in 10 to the power minus 3, so 10 to the minus 6, how much is that? So now, guys, if you look, they are saying that this is there in 1 kg of water per kg of. Oh, million means 10 to the power 6, no? 10 to the power 6. So they are giving you in per kg. That means these many grams is there in 1 kg of water is something that they are saying. That means, guys, how many grams of water? 3 into 10 to the power minus 3 grams of calcium carbonate is there in 1000 grams of water. Right, Ritik, right? 1000 grams can be written as 10 to the power 3 as well now. I want the value in 10 to the power 6, correct? Parts per million. So in 10 to the power 3 grams, I have this. In 10 to the power 6, how much? Parts per million. So parts per million grams of water. It's what they want. This would be, just do the unitary method. Right? They would cancel out. They would come as 10 to the power 3. So the answer is P, P, P.
Sir,
Yes.
could you scroll above?
Yeah.
So, when you multiplied 3 into 10 power of minus 4 into 100, should it not be 3 into 10 power of minus 2?
Correct. Minus 4 into 100 is minus 2. If it is minus 2, right.
The answer might be then 30 ppm.
30 people. Yeah. So guys, if you look into the question, there is nothing in this question. It's just the arrangement part is the thing that is taken. So first you find out the number of moles. Whatever the number of moles of that system is, that is equivalent to the similar number of moles of calcium carbonate. you convert it into grams and make sure that you are finding out in um, parts per million. So 10 to the power 6 grams of water. No, they are given you in 1 kg. That means 10 to the power 3 grams of water. Converting into 10 to the power 6 grams. So that gives you the. To solve one or two questions like this, you will be often. Okay, guys. So this was the only thing. Now go to the hydrogen peroxide segment once. Give it a reading. I guess you will be fine. Okay. That was the entirety of this chapter, guys. Give it a reading, and if you have any doubts or anything, you have my number. You can reach out to me, or you can definitely apply for some PR sessions. Okay, let's keep it up to this then, guys. Bye, everyone. Good night.
Thank you, sir.
You're welcome,
Sir,
Beta. Yes.
thank you, sir. So
Okay.
for the ortho and para nature of H2, like, could you explain like how does energizing the hydrogen uh, change its spin?
So, Beta, actually, what happens is, just 1 second. Will not be having. Not now. Let me just complete all the day advanced segments. What's happening? Right? What actually happens is better that the spin of a particular system depends on the energy. Okay. So as you know that, like I have told you before as well, when you have a high energetic compounds, the spins are called high spin compounds. What actually happens over there is when you have parallel spins of electron, that is of higher energy. You have learned in atomic structure. There you have learned that when the electrons are actually having both the opposite spin, they are having comparatively lesser energy because the magnetic property gets cancelled in that. Let's say there is a charge moving. You know, when the charge is moving, they will be creating a magnetic nature in that. You have learned the Fleming's left hand rule in there. Whenever there is a movement of charge, there will be a magnetic property getting generated. So let's say
Yes.
for a clockwise spin, you are getting the magnetic property getting generated in this direction. So for the anti-clockwise spin, the magnetic property would get generated in the opposite direction. They would cancel out each other. That's why opposite spins are more stable than parallel spins. So when you talk about a system in lower energy state, their spin is opposite. But when you excite that molecule, you can definitely change the spin multiplicity to the parallel spins as well. That is what happens in octane para.
Got it, sir. Thank you.
Welcome. Bye. Welcome. Bye.